software supply chain attacks, they're not just some theoretical thing anymore, are they? They're really happening.
Oh, absolutely. And the data is, well, it's pretty alarming when you look at it.
But like that Verizon 2024 report, breaches from third-party software dev jumped, what, 68% in 1 year?
Yeah, a huge leap. And if you look specifically at malicious packages in open source managers, Reversing Labs tracked like a 1,300% increase.
1,800% over just 3 years.
Exactly. It really shows how much the software supply chain is, a prime target now. And that attack surface is just ballooning.
It really puts the scale into perspective. So today we're doing a deep dive into a very specific and maybe kind of surprising vulnerability area within all that.
We are. We're looking at the security risks around self-hosted GitHub Actions runners.
Right, particularly when they're hooked up to public repositories. That seems to be the kicker.
Precisely. And our sources for this are pretty interesting. We've got the usual industry reports, technical docs. But what's really compelling, I think, are these transcripts and notes from Black Hat talks. These are from the security researchers who didn't just theorize about this stuff. They actually found and exploited these exact vulnerabilities.
Wow, so real-world exploits on high-profile targets.
Yeah, some really eye-opening examples we'll get into.
Okay, so our mission today is to sort of unpack this. We want to help you understand why these self-hosted runners, set up in certain ways, can be so dangerous.
We'll walk through those real-world case studies, the ones that make you go, wow.
And then, crucially, talk about what you, the listener, can actually do to protect your organization, or even just your own projects.
Because, let's face it, CI/CD pipelines, they're central to how software gets built these days.
Totally.
A weakness here isn't just some minor bug. It's potentially a direct route for attackers, stealing IP, disrupting development.
Or worse, injecting malicious code into software that, thousands or millions of people might end up using.
Exactly. So whether you're the person managing the infrastructure or you're writing the code, or honestly, even if you just care about where your software comes from.
Understanding this specific attack vector is, well, it feels essential now.
Agreed. Let's dive in.
Okay, so maybe let's start with the basics. Just level set for everyone. What exactly are GitHub Actions and these runners?
Sure. So GitHub Actions is basically GitHub's way of automating stuff in your software workflow. Think CI/CD, continuous integration, continuous delivery.
Yeah, right. Building code, running tests, deploying things.
Exactly. All those repetitive but critical tasks.
Okay. And these automated workflows need somewhere to actually run, right? That's the runner part.
That's it. The runner is the execution environment. And there's two main flavors.
Okay.
First, you've got GitHub-hosted runners. GitHub manages these completely. They spin them up for you, keep them updated weekly.
Major operating systems, different architectures, all that.
Yep. And the key thing here is they are always ephemeral.
Ephemeral meaning disposable.
Exactly. After your job finishes, that environment is completely torn down. Poof, gone. Next job gets a totally fresh, clean environment. Security is largely handled by GitHub.
Okay, that sounds pretty secure. Like a fresh sandbox every time.
Yeah.
So what's the alternative? The self-hosted runner.
Right. Self-hosted runners are different. They run on machines you manage.
Yeah.
Could be a physical server, a VM in your cloud, whatever.
Your infrastructure?
Your infrastructure. You install the Actions Runner agents software on it. You connect it to GitHub, and you manage it.
And the big difference then, apart from who manages it?
The security responsibility is entirely on you.
Ah, okay.
And critically, unlike the GitHub-hosted ones that always disappear, self-hosted runners can be set up as either ephemeral or non-ephemeral.
Meaning they can stick around, persist between jobs.
Exactly. They can run one job, then sit there waiting for the next one, potentially holding state or, anything else left behind.
Yeah. And the sources said that non-ephemeral option is the path of least resistance for attackers. So why do people even use self-hosted if it adds this security headache? Seems like a big trade-off.
Well, there are legitimate reasons. Sometimes it's about compliance or data privacy, needing to keep builds totally internal off GitHub's infrastructure.
Made sense. Sensitive data.
Or maybe you need specialized hardware. GPUs for machine learning, specific chip architectures for embedded systems or IoT devices, things you just can't get on the standard GitHub runners.
Right, niche requirements.
Unusual OS versions, maybe. And sometimes, organizations think they can save money by using hardware they already own.
Okay, so valid reasons exist, but you're definitely taking on that security ownership.
And this is where the research, particularly from those Black Hat talks, gets really interesting. It highlights a blind spot many seem to have.
Okay.
The researchers scanned millions of public GitHub repositories.
Millions. Wow, that's comprehensive.
Really is. And they found tens of thousands using self-hosted runners.
On public repos, where anyone can see the code, anyone can interact.
Exactly. That's the crucial point. With a private repo, access is limited. With a public one, any GitHub user can potentially poke at it, usually by opening a pull request.
So the potential attack surface just explodes. It goes from your internal team to basically the entire internet.
Pretty much anyone with a GitHub account. And what makes it worse is attackers can actually learn a fair bit about your self-hosted runner setup just by looking at the public workflow logs.
Really?
Yeah.
What kind of stuff leaks out in those logs? I thought they'd be fairly clean.
You'd be surprised. You can often see the runner labels used, figure out if it's an org level or repo level runner, maybe even glean the machine name or runner group.
Okay.
You can see the permissions that the GitHub token has, especially the permissions used by later legitimate workflows running on the same runner.
Ah, so you can see if subsequent jobs are highly privileged.
Sometimes, yeah. And just by watching how code checkouts behave, you can often make a good guess if the runner's non-ephemeral, sticking around between jobs. Even the architecture might leak.
Wow. That's a lot of reconnaissance information just sitting out there in public logs.
It absolutely is for anyone looking. And the sources really pinpointed why this combination public repository plus self-hosted runner is just so risky.
What are the core reasons?
Well, first, people tend to stick with default settings. And the defaults, especially around workflow approvals for public repos, often aren't secure enough when you're dealing with potentially untrusted contributions.
Default insecurity. Classic.
And second, this one is really key and maybe counterintuitive, becoming a contributor to a public repository. It's not really a security boundary in these vulnerable setups.
Wait, hang on. Becoming a contributor isn't a security boundary. I always assumed that meant someone was, at least somewhat trusted or vetted.
The researchers were very clear on this point. In the configurations they exploited, the system doesn't treat contributor status as a meaningful security gate for running workflows.
So how easy is it to become one?
Often. Incredibly easy. Merging just one pull request, maybe fixing a tiny typo in the RIADME file, that's enough.
A typo fix.
Yep. Anyone can submit a PR for a typo. It gets merged quickly because it seems harmless, and boom, that person is now flagged as a contributor.
And that simple act opens a door if the other vulnerable pieces are in place.
Precisely. It can be the critical first step for an attacker.
Okay, so let's piece this together. The sources mentioned a vulnerability triangle that enables these really bad incidents. What are the three corners?
Right. It's a specific dangerous alignment.
Yeah.
First corner, the default workflow approval settings for public repositories.
Okay.
By default, if a pull request comes from someone who's already a contributor, the workflow triggered by that PR often just runs automatically.
Yeah.
No manual approval needed for the workflow itself.
Ah, okay. So I fix a typo, become a contributor, then I open a new PR, maybe with a sneaky change to a workflow file, and that workflow might just run without anyone checking the workflow code itself.
That's exactly the problem. That's the first side of the triangle. Second side, the presence of a non-ephemeral self-hosted runner.
The persistent one that sticks around.
Right. Because it persists, if an attacker gets code execution on it once, they can potentially stay there, they can plant something on the runner and wait.
Okay, so automatic execution for contributors, plus a persistent machine. What's the third side?
The third side is that subsequent legitimate workflows, the ones that run later on that same persistent runner, have overly permissive GitHub tokens or access to valuable secrets.
I see. So the attack path is 1, become a contributor easily, maybe with a typo fix.
Yep.
2, submit a PR with a malicious workflow change that runs automatically because you're now a contributor.
Runs on that non-ephemeral self-hosted runner. Yep.
3, use that initial execution to get persistence on the runner, maybe install a backdoor or something.
It's exactly. Plant your flag.
And 4, just wait until a legitimate higher privilege workflow runs on that same compromised runner.
And then your persistent code intercepts the secrets or uses the higher privileges from that trusted workflow.
Wow, okay, that makes sense. It's a chain reaction exploiting defaults and persistence.
And it sounds theoretical, but the researchers demonstrated this with devastating effect in the real world.
Right, let's get into those case studies. They sound pretty wild. The first one, they actually targeted GitHub itself. Seriously.
Yeah, this one from the Black Hat talk is probably the most jaw-dropping because of the potential scale. They went after the actual GitHub repository used for building the images for GitHub-hosted runners.
The images used by potentially every GitHub customer.
Exactly. If you compromise that, you could potentially compromise well, almost everyone using GitHub Actions.
Okay, the stakes couldn't be higher. How did they get in? Was it some super complex exploit?
Nope. Shockingly simple. Again, exactly what we just described. They became a contributor by fixing a simple typo in a documentation file via a pull request.
It's just a typo fix.
It got merged quickly, seemed harmless. They were in it as a contributor.
Unbelievable. Okay, so they're a contributor. How did they leverage that?
They found that nightly CI workflows in that repo used non-ephemeral self-hosted runners. And crucially, those workflows ran with highly privileged tokens, specifically full write tokens.
Ah, the trifecta. Contributor status, non-ephemeral runner, high privileges.
Bingo. They got a malicious workflow change merged, it executed on the runner, and they achieved persistence on that machine.
Persistence on a runner building images for all GitHub customers. What could they have done? What was the potential impact?
It was massive. They demonstrated they could access critical secrets. One secret they found could potentially approve and merge any pull request, including more malicious ones from the attacker themselves.
Whoa.
They showed lateral movement capabilities into GitHub's internal infrastructure, like their vCenter environment. They could potentially tamper with the runner image build process itself, a catastrophic supply chain attack scenario. Pipeline privilege escalation.
All stemming from fixing a typo? That's sobering.
It really is. The second case study, breaching Microsoft's perimeter, reinforces the ease of this type of attack.
Easier than the GitHub one? How so?
Well, the researchers specifically pointed out that this didn't need deep CI/CD knowledge, no complex social engineering, no fancy web exploits. Again, it boiled down to fixing a typo to get contributor status.
Just leveraging the system's defaults and trust model. What was the target at Microsoft?
There's a public AML repository they maintain called DeepSpeed.
AML repos.
Yeah.
Why are they common targets for this?
The researchers noted a couple of things. AML often needs beefy compute, lots of GPUs maybe, which pushes teams towards using self-hosted runners for specialized hardware.
Right, makes sense.
Plus, AML development can move really fast, and sometimes, security configurations might get overlooked or shortcuts taken in the rush.
Okay, so they targeted DeepSpeed, same pattern, typo fix, contributor, malicious workflow.
Exactly the same playbook. Fix a typo, become a contributor, submit a PR with a workflow change designed to run on their self-hosted runner.
And the impact this time. What did they achieve inside Microsoft?
By getting code execution on that runner, which was presumably inside Microsoft's network boundary,
Right.
they effectively got a foothold directly onto Microsoft's internal network.
Wow.
And not just any foothold. It came with the privileges of a senior developer account. That opened the door for potentially significant lateral movement, privilege escalation within their Active Directory. Essentially, a relatively easy perimeter breach.
Okay, the third case study sounds perhaps the most alarming, targeting a major U.S. chip manufacturer. The researchers used this phrase, could shape the course of the world. That's heavy.
It is. And it underscores the criticality of the target, a key player in the domestic semiconductor supply chain. Here, the initial access vector was a little different.
Oh, not the typo fix this time.
They didn't need the typo fix contributor status for the initial code execution, interestingly. They found a workflow using the pull request target trigger.
Okay, remind me, pull request target. That's the one that runs in the context of the main repo, not the fork, right? And has access to secrets.
Exactly. It's designed for things like automatically labeling PRs or running checks that need secrets, but it's inherently risky because it processes code or input from an untrusted fork while having access to the base repo's secrets.
So how did they exploit that here?
This workflow ran a common testing tool called Tox, but it was configured in a way that Tox ended up processing configuration files or test files directly from the attacker's untrusted fork.
While the workflow itself had access to secrets.
Yes. So by crafting malicious content in those config or test files within their fork's PR, they could essentially inject commands that Tox would execute within the trusted secret-holding workflow environment.
Clever. Okay, so that was the entry. What were the underlying weaknesses that allowed this? Still the self-hosted runner.
Yes, the familiar pieces were there. An overscoped classic personal access token, a PAT, being used as a secret.
Oh, personal access token. Okay.
A non-ephemeral self-hosted runner connected to this public repository. And this pull request target workflow allowing secrets access to code from forks without proper safeguards or review.
Got it. And the escalation. You mentioned that, Pat, the action token. What was so special or dangerous about that specific token?
This is where it just goes off the charts. That one PAT turned out to belong to an enterprise admin bot account.
Enterprise admin.
With organization owner level permissions across all of the company's GitHub organizations. Not just one, all of
Oh
them.
my God. Owner across everything.
Everything. Apparently, even some internal security rule sets they had weren't configured tightly enough to fully prevent bypassing protections when using a token this powerful.
So what could the attackers do with that level of access?
Basically anything they wanted within the company's entire GitHub footprint. They had admin control over more than 16,000 internal repositories, many highly sensitive, given it's a chip manufacturer.
16,000 repos.
They could have made them all public with a script. They could have potentially deleted the entire GitHub organization, wipe out over 120,000 repos instantly. The potential for catastrophic damage was just immense.
That's almost unimaginable access from one compromised token.
And this case really hammered home the issue of poor Pete hygiene that the researchers found was widespread in organizations they audited.
What kind of hygiene issues?
Just tons of active PTs floating around, many with way too broad permissions like owner. And critically, a huge percentage, they showed metrics like over 79% in some orgs, had no expiration date.
No expiration, so they just live forever unless manually revoked.
Exactly, making them perfect long-term targets for attackers. Plus, a lack of specific audit logs for just enumerating or listing PTTs made it hard for defenders to even know what tokens existed or if someone was trying to find them.
Wow. Okay, these case studies are incredibly powerful illustrations. So let's pivot to defense. Given how bad this can get, what can organizations, what can you, the listener, do to defend against this continuous integration, continuous destruction, as one researcher put it?
Well, the strongest, clearest recommendation coming out of all this research is pretty blunt. You should almost never use self-hosted runners for public repositories, period.
Just don't do it if you can possibly avoid it.
The risk profile is just fundamentally different and much, much harder to manage securely compared to private repos. If you are using them for public repos right now, that needs immediate, urgent review.
And even for private or internal repos, they said, use extreme caution.
Absolutely. The principles still apply, just the attack surface is smaller, but you still need careful configuration.
Okay, so priority 1, avoid for public repos. But if you must use self-hosted runners, maybe for those hardware reasons, or you need to secure your existing private repo setup, what are the key steps?
First, for public repos especially, enable workflow approval requirements for pull requests coming from external forks or first-time contributors.
Force a human review of the workflow code changes.
Yes. Break that automatic execution link in the chain. Second, whenever feasible, use managed ephemeral runners like the GitHub-hosted ones.
Stick with the clean slate.
If you absolutely need self-hosted, put in the engineering effort to make them ephemeral. Configure them to run one job and then self-destruct and be replaced. That eliminates the persistence threat.
Okay, ephemerality is key. What else?
Rigorously apply the principle of least privilege. This is huge. Your GitHub token that workflows get automatically. Default its permissions to read only.
Don't give it write access unless absolutely necessary.
Exactly. Only grant specific minimal permissions and only scope them to the specific jobs that actually need them. Same goes for any other secrets used in workflows. Limit their exposure.
How do you limit secret exposure effectively?
Use GitHub environments. You can configure environments, say, for production, put your sensitive deployment secrets there, and then require specific reviewers to approve any workflow job attempting to run in that environment and access those secrets.
Ah, another human gatekeeper for sensitive operations. That sounds really useful.
It's a critical control. Also, a simple but vital rule. Never share self-hosted runners between public and private repositories.
Don't let a compromise in public bridge to private.
Correct. And similarly, try to segregate your continuous integration build test workflows from your continuous delivery deployment workflows. Don't run sensitive deployment jobs on the same runners used for general PR checks if you can help it.
Keep those higher privilege CD tasks isolated. Makes sense.
Use runner groups and configure access control strictly. Define which specific repositories or even which specific workflows within a repo are allowed to target a particular runner group. Don't let any repo use any runner.
Granular control.
Absolutely. And audit, audit, audit. Regularly review your secrets and especially your personal access tokens. Check their scope. Is it overly broad? Do they have an expiration date? Track their usage.
That Pate hygiene again.
It's critical. Use features like code owners files. You can specify that changes to certain critical files, especially your workflow YAML files, and .GitHub workflows require review and approval from specific security teams or senior engineers.
Add required reviews for workflow changes. Good one.
And don't forget monitoring the runners themselves. If you're running self-hosted runners, you need visibility. Use endpoint detection and response (EDR) tools on those machines.
EDR to spot suspicious activity on the runner itself.
Yes, like unexpected processes, network connections, attempts to tamper with files. Also, while GitHub's audit logs are getting better, make sure you've enabled IP address logging in your org settings. That's crucial for spotting credential theft or misuse attempts.
Okay, and what about those specific secret handling practices the sources mentioned, beyond just scoping?
Right, some finer points. Avoid putting structured data like JSON or complex strings directly into secrets. It makes it really hard for systems to reliably redact them if they accidentally get logged.
Simpler secrets are safer.
Easier to redact reliably, yes. Also, make sure you actually register all sensitive values used in workflows as secrets, even things derived from secrets, or encoded versions like base64. This gives GitHub's redaction engine the best chance to catch them in logs.
Tell GitHub what to look for.
Exactly. And manually review logs after testing workflows that handle secrets. Don't just assume redaction worked perfectly. Look for leaks. Be mindful of script injection risks too, especially with inline scripts processing untrusted input, like PR titles or commit messages.
How do you mitigate that?
Pass untrusted input through intermediate environment variables rather than directly substituting into script commands. Even better, use dedicated actions from trusted publishers, as they often handle inputs more safely than inline scripts.
Okay. And finally, circling back one last time to that chip manufacturer case, the P8Ts.
Yeah, that P8 hygiene point cannot be stressed enough. Audit your P8Ts now. Find the ones with broad scopes, especially organization owner. Find the ones with no expiration dates. That 79% plus figure is terrifying.
Terrifyingly common, it sounds like.
It seems so. This needs rigorous, ongoing auditing and a serious cleanup effort in most organizations, based on what the researchers found. Set expirations, enforce least privilege, revoke unused ones.
Okay, so let's try and bring this deep dive together. If you had to recap the core message from all this research, especially those black hat talks, what would it be?
The researchers had a few key sound bites that really stuck. First, continuous integration, continuous destruction is systemic, meaning this isn't just a few isolated incidents. The problem is widespread, often stemming from a lack of awareness of these specific risks.
It's built into the way many people are using these tools by default.
Exactly. Second, public GitHub repositories are in the crosshairs. Attackers know these configurations are common, and they are actively scanning for and targeting public repos as an easy entry point.
You're looking for that open door.
They are. And third, perhaps the most direct. Ignorance is breach.
Ignorance is breach. That's powerful and a bit chilling, frankly.
It really is. It highlights that not knowing about these vulnerabilities, not understanding how they can be exploited, is practically inviting a security incident.
So this deep dive, it wasn't just about sharing scary stories. The goal was really to arm you, the listener, with that specific knowledge, understanding how these attacks work, using those real examples.
So you can then look at your own systems, your own pipelines, and spot these potential weaknesses before an attacker does.
And this isn't just for the security team, right? Developers writing workflows, ops managing runners, everyone involved needs to grasp this.
Absolutely. Understanding this vector, the self-hosted runner, public repo, contributor status, permissions interplay, it's fundamental to improving your software supply chain security posture.
So maybe the final thought to leave you with as you finish listening, where might that ignorance be breach in your own environment?
Where are you using self-hosted runners?
Yeah.
Are any attached to public repos? What are your default workflow permissions? When was the last time you audited your PATs?
How can you start looking at your development pipelines, your repos, your secrets, not just for functionality, but through the eyes of an attacker searching for that path of least resistance you might have unintentionally left open?
Use these case studies, this knowledge, to proactively question and review your setup. Don't wait to find out the hard way.